So our, well, I should give you a very, very brief introduction, which I forgot to prepare for at all. But our speaker today, RobertBrunner, is from the Department of Astronomy here at this beloved campus, but nevertheless did have to walk outside in the snow to get here. Robert's been working with Tom Long on problems related to sort of computer vision over time, or how do complex multidimensional signals that also change over time? How does that change your understanding of the universe? And so, before doing it, please.
Thank you. So you didn't even say how we met.
Oh, I didn't actually.
We're working on a proposal for crowdsourcing and maybe for an application for crowdsourcing. So I'll actually briefly talk a little bit about that crowdsourcing application. And since I don't know the level of background everyone has, I'll try to give a little bit of background and justify why here. I also have this little symbol. I'm also a faculty member in statistics, and so things that might be relevant here, I sort of show this little symbol to say, hey, this is something where we don't know the answer. So if you're ever going along and saying, I wonder if they really know this, well, if you see that symbol, then no, we don't. So what I'm going to talk about, I'll give a quick astrophysics background, then I'll talk a little bit about cosmology and machine learning while we're doing that. There'll be a little bit of discussion about crowdsourcing then. Then I'll talk about synoptic astronomy, which is what is probably most relevant here in terms of the fact that we build up signals of how the brightness of objects change in time. And then I'll very briefly sort of highlight that thing. So why am I even here? Why are people excited about astronomy? Well, why have to answer that question, right? It's how many people get into science?
You have a sympathetic crowd here for that.
Yeah, I was going to say, seriously, right? I mean, this is what we do, right? There's my office. But no, I mean, right? So we're fascinated by space and the prospects of that. In fact, I'm teaching right now a course that's called Search for Extraterrestrial Life, and I know that's kind of a wait a minute. That's really a official University of Illinois course. Yes, it is, and we approach it as scientists. And we try to identify what are shortcomings and sort of limitations of our knowledge in actually answering that question. And it's a lot of fun, but it's also rather educational. And so it sort of brings that whole idea in that the universe is big and there's lots of possibilities, and we'd like to know more about it. But a little more closer to home, another reason I think it's quite interesting is this. This is actually a picture of the surface of Mars. Now, when I talk to students in my intro classes, I always show things like this. And it's hard for me to appreciate because they have never, and maybe some of you have never not been able to see pictures of other planets. But this is an incredible change for humanity to be able to do, right? To send probes to other planets, other things in our solar system, and take pictures and bring them back with the clarity that you can feel like you're standing there. About 7 years ago or so, the PI of the Mars rover projects was here, and astronomy has a distinguished lecture series. He was here presenting for that, and he brought images with him from that, and they put it on the NCSA wall, the big visualization wall, and you could literally walk up next to this wall, and it would be like in a window at a building on the surface of Mars, that you were just totally surrounded field of view by Mars. And to me, personally, it was a very moving moment, just to sit there and feel like that, right? I mean, when I was a kid, that was my dream, to be an astronaut. It didn't happen. I'm firmly rooted on the ground. But there's still that thought, right? That's a possibility. So that's sort of a bit of the sort of motivation-wise. So let me give a little bit of a background what I'm talking about. So when we think about astronomy, there's a lot of things. The universe is very big, so I want to just highlight certain things that we talk about. Each of these have components of synoptic astronomy when we get to that. This is the potentially habitable exoplanets. Again, it's mind-blowing for me. When I first started teaching Search for Extraterrestrial Life about 4 years ago, we would talk about exoplanets, which are planets around another star, and we would say, we know of a few candidate planets around other stars, but we haven't really found any that would be like Earth-like, so it's bringing a lot of uncertainty. And now, literally about once a month, they update this figure. Okay, this is from January. The previous one was from December, and it's just showing you, right? We keep getting new ones. So for reference, these are the size of our solar system planets. There you see Earth. The idea is that if something is like Earth and in the right distance from its star, it would be capable of having liquid water and thus supporting life, which would probably be the discovery of our lifetimes finding planets that could hold life. Then you start saying, do they have signals? Right? Would they be intelligent? And then Mark's whole research would turn to, how do we communicate with an alien life on this planet?
That would be a neat direction to go into.
You want to try to understand the language. Forget about the Indian languages or whatever else. I mean,
yeah.
How would they even communicate? Right?
Yeah.
We actually discussed that in my class.
Mismatched crossword singing. Yeah, take those signals and see if they can. Yeah, absolutely.
And then you got an alien crowd you're trying to this sort of stuff too, right? So these sort of show different planet sizes, and they also have this what's called a habitability index. The closer it is to one, the more like Earth it is. But it's sort of shown here now. They're ordered by distance from us. Okay, so this is the closest one. Is 12 light years away. Seems pretty close. 12 light years is, of course, the distance it takes light to travel a year, right? So that's 12 years it takes light to travel. If they sent a signal, it would take 12 years to reach us. Okay, so when you figure out what to send them back, it would take 12 years for that signal to go back to them. Assuming they could understand you, that would be another 12 years. You're talking 24, 25 years to maybe get a response to your signal. I don't know how long our academic careers would be, but that would really be pushing it. Certainly not a good for a tenure decision, right? And then, of course, you see the numbers go out. Now, interestingly enough, that is not the closest planet to us. The closest planet to us is actually around the nearest star to us. Not the sun, but the nearest star to us, Alpha Centauri. There actually are planets in that system. It's not a single star system. There's multiple stars, but there are planets in there as well. So the interesting thing is we now believe every normal star has planets. Okay? It used to be just a few years ago, we had no idea. Now, we think they all do. We think it's just a natural thing. And so then you start thinking about the prospects of life and that, and the prospect is certainly not trivial or non-negligible. Okay, so there's exoplanets. I don't study exoplanets, unfortunately, but they're still quite fascinating. There's other galaxies, right? We live in a galaxy. There are roughly 200 to 400 billion stars in our galaxy, and there are even more galaxies in the universe. So there's many of them. They're beautiful. There are black holes. I did not actually brought any sound. I don't know if you really hear it. That's the sound of a black hole. That's my one audio signal for you. Gratuitous audio signal. That is not sound as you would normally. It's actually X-ray observations, and they've turned that into sound. But black holes do make sound. And we've seen them. This is an example of it here. This is actually a supermassive black hole, so it weighs about the equivalent of 1 billion solar masses. And it's very energetic, very dynamic, and it pulses energy out, and those cause ripples in the matter around them, which are just pressure waves, sound waves, in the surrounding medium. All right? So here we're seeing it, that you can actually think about these just like that, sound waves propagating out. Same physics applies. You have pressure waves moving in a medium. That's a very large black hole. These are very, very low frequency because it's taking 1 billion years for that to propagate out. So in hertz, that would be 1 nanohertz or something like that. But black holes, even closer in, do have sound, right? They are affecting their nearby medium, and they do things. So you can Google and find all you want. Black holes, obviously, something else that's very interesting. More of what I study is cosmology, which is trying to understand how the universe forms and evolves. What's going to happen to the universe. So we look at very distant pictures of the universe, something like this. We see things. If you look at this, your eyes very carefully, you'll notice some strange things like that, right? You say, what somebody had their thumb on the camera? Why are we getting this? That's actually a background galaxy that has been lensed by the foreground objects and distorted, right? Finding things like that is extremely important and precious. We want to do that. An even more precious thing is the fact that we have this, and this. There are the same object appears multiple times in this image. And that actually gives us a great way to probe what's out there, what's actually out there, dark matter, dark energy, finding things like that. And as you can see, that's a non-trivial problem, because if you just look at this, how would you know? Right? And this is an HST image, which means it's the highest quality we have. Ground-based images, it's even harder. And so one way we do that is we take pictures over time, repeatedly, and we start to see how they vary and see, do they vary the same way? So in other words, are the signals that we're receiving from them the same? Now that sounds easy, but you have to remember that we can only get our signals when it's no clouds, when it's not snowing, right? And when our object's up in the sky. So there's strange things that affect our signals. And then I just want to make the point, it's a very big universe, and there's lots of stuff out there. So what do we do when we're getting data? Fundamentally, we focus on the electromagnetic spectrum when we're getting our observations. Of course, the spectrum goes from radio out to gamma ray. We see here in the visible, just sort of roughly showing. That's how traditionally astronomy has worked. We do a little bit with fundamental particles, so people do observe neutrinos, for instance. But a new door that's opening that maybe in 10 years I would be back here talking to you about is gravitational waves. And why am I saying that? Because gravitational waves are effectively sound waves in space-time propagating out. So many of the things you talk about in signal processing of audio sounds translate right into a gravitational wave spectrum, looking for certain features. And what causes those tend to be things like black holes that are orbiting each other. You can imagine sticking 2 fingers in water and twirling your fingers back and forth. They create ripples in the surface of the water. It's the same thing here, but now it's actually in space-time, which is.
So you're comparing it to sound because it's, because by comparison between gravity and pressure in a medium, or.
Well, this is effectively these objects are distorting space-time. Just like a massive object, which would be moving in air, for instance, a speaker or something would be distorting the pressure, right?
Are they compressive waves the same way that sound is?
It's slightly different because these are truly spherical waves, and there is decaying and there's a back coupling, but fundamentally yes, right? Especially the way you measure it, because you measure it with. That's one thing you say. How do you measure variation in space-time? You actually have to have an object which is accurately measuring distances, and you look for that distance to change because space-time has stretched them apart. And so they typically use laser interferometry, which is very accurate, and so you have lasers shooting in different directions, you recombine them, and you see, did the distance change at all while I was doing that? And you have to be very careful because what is a contamination signal? It actually is things like sounds, like earthquakes, pressure waves, trucks driving by on the highway. So you don't put these, in an urban area, you put them in a remote area. But yeah, you fundamentally have that compression rarefaction in space-time.
Could transducers like this be put in some place like Hubble?
Okay, so the short answer is, can you put this in space? Yes. There actually are projects to do that because fundamentally that's what you want. Problem is you start adding zeros to the price tag anytime you do that. Mm-hmm. It's roughly $1 billion to even think of putting something in space. It's a serious instrument, not some small instrument. So there is some plan to do that. The problem there, though, is how do you keep? You have to have at least 3 satellites and have 2 base arms, and how do you keep them in sync with each other? Because you're going to put them like a kilometer apart or something, so you can't tether them. I mean, it's an engineering issue, which is beyond me. But yes, that is the plan. Because that would allow you, because as you know, the longer your baseline, the more sensitive you are to certain frequencies, and those are the frequencies we want to push to as we go down. All right, and this actually is something called multi-messenger astronomy, because anytime we do something in astronomy, even whether we're looking at gamma rays or X-rays or radio waves, whatever, we always want to come back and say, well, what was it that caused that signal we saw? And traditionally, we always come back to optical, right? In part because that's our detectors. But also in part because stars, which are one of the main things that cause issues like this, that turn into black holes, emit in the optical, emit lots of energy in the optical, so it's easy to find them and locate them. And so you detect, so this is actually something that will be coming on in the next few years, the LIGO Observatory, and there's this big plan. They detect anything, everybody stops doing what they're doing and moves their telescopes to try to figure out what was actually doing this, because this is a really, really important thing. Okay, so back to the spectrum data, the spectrum. Right, visible, what we see in the full electromagnetic spectrum. We only see in a very tiny part what we focus on. We actually now in astronomy observe all over the spectrum. And I'll make 2 points, because I'm going to show you what the sky looks like in microwave and what it looks like in gamma ray. But first I want to talk a little bit about stars. Typically we want the actual spectrum, the amount of energy emitted as a function of wavelength. Okay, so that's our spectral signal. But it's hard to get that. It takes a lot of telescope time, and we don't have a lot of telescope time. So what we do is take pictures and try to reconstruct that. But you can see, just looking at a spectrum of different types of stars, how the spectrum changes. So for instance here, These are absorption lines. There's cool gas in the outer parts of stars that absorbs gas. So those absorption lines give us unique features, and there's other ways to tell the difference. But fundamentally, that's what we're after. If we can see those pictures of objects in different wavelengths, we can see it. So here's an example of that. Here is a spectrum of some object. And then here are the filters we actually observe through. So any light that makes it through that filter, we get in our picture. And then we can calibrate, we can say, there was so many photons that made it through. And then we basically get a rough measurement of, okay, the spectrum would have been right about here. And there would have been another point here, and another point here, and another point here. So you can see we take basically several thousand elements of the spectrum, turn it into 4 or 5. The difference is that I can get pictures of about 10,000 objects in 4 or 5 bands like this in the time it would take me to get one spectrum. Okay, so 10,000 beats 1. If you do it enough, you get the statistics, you can do that. These were just pictures of this Sloan Digital Sky Survey telescope and camera. Used 30 CCDs that actually got us this data. Interestingly enough, as an object gets farther away from us, its redshift, its measurement of its distance from us, gets bigger, and that also causes the object spectrum to shift to the red, hence the red shift. And so as we do that, you can see that the amount of energy coming through these filters changes. Right? So here at low redshift, the blue is the low redshift, right? There's a lot of energy over here. As it gets farther away from us, it's out here, more of the energy's in the R. As it gets even farther away, more of the energy's out here. So you can already see how these measurements in U, G, R, I, Z give us a rough way to estimate that distance, which can be very useful when we're trying to figure out where galaxies are. All right, here is a map of the sky in microwaves. Right? Of course, this is a projection, a Maui projection. There would be the actual, if you thought about it in terms of a sphere. Astronomy is like GIS, except we just point up instead of down, right? We're inside the sphere instead of out. Here's a picture of the sky in the gamma rays. Okay? So when I show you this in the gamma, first thing you notice is there's this thing going right through the middle. That is our Milky Way galaxy. Right? The Milky Way emits in all different wavelengths. It had been statistically subtracted out of the microwave map I just showed you. You notice some different things, right? Unidentified. Don't know what that is. The sun. The sun actually emits gamma rays. Interestingly enough, the sun, of course, moves. Actually, we move around the sun, so its apparent position in the sky changes, and you can see the track of the sun through here. Then you see some other objects out here. Interestingly enough, you'll see something like maybe here. Right? This is something that's in our galaxy. Right? Here's something that looks just about the same brightness. This is in gamma rays, so these are extremely energetic photons coming, right? This is roughly 1 billion light years away. So if it looks the same brightness as this, it means it must be extremely luminous. And it is. It's powered by a supermassive black hole. It's pulling stuff in, falls in, it gets very hot. And it seems odd, right, that a black hole would emit a lot of radiation. It's not the black hole that's doing it, it's the surrounding environment, but we have that. So that's interesting. This is fairly new. We haven't been able to do this, observing the gamma rays across the whole sky. There's a satellite, Fermi satellite up that's doing that. We can see that. Okay, so I've shown you a little bit of background about actually what data we're trying to get. Let me quickly mention, though, what's happening. So we have something out there that's emitting light, right? And we have to try to deconvolve all these issues. So what's happening as the light travels to us, right? I'm sure you have the same things, you know, in terms of processing signals, right? Is the microphone picking up things well? Are they speaking clearly? We have the same issues, right? We have issues that are out in space that affect our signal. We have, once it hits the Earth's atmosphere, it affects our signal, right? You can notice on some nights stars look really, clear, and other nights it's a little fuzzy. Our atmosphere distorts things, so we have to try to fix that. Then we have our detectors. What are our detectors doing to our signal? In astronomy, we almost always, especially when we do cosmology, almost always are in what's called the low light domain, okay? So we don't have high signal to noise data. We rarely have high signal to noise data. Most objects are very faint. So we do that. We try to recover all of that out to get what is that true intrinsic signal. The fundamental thing we use is actually CCD detectors, charge transfer detectors. Typically, they're 2K by 2K, so it's 2,000 by 2,000 elements. Although nowadays, we often use 4K by 2K. We used to use just one. Now we build cameras with many of them. So for instance, the Dark Energy Survey, which I'm a part, it's actually processed and archived at NCSA that uses 70 of these 2K by 4K CCDs. So every time you take a picture, you have 70 of those coming in and giving you results. It's a lot.
Can I ask you, I don't know if you're going to cover this, but on the previous slide, all of the different channel responses that this goes to. How of these channel responses? You talked a little bit at the beginning about how the first one, distortion by the
you mean these filters, or did you mean the actually effects of the atmosphere?
The propagation affects interstellar medium, that you talked at the beginning about how that's one of the things that you actually want to look for, because it can tell you about dark matter. The instrument itself, that must be something that you can.
Yeah. So what Mark's asking is, right, this light's coming to us, and stuff's happening to it along the line of sight, right? So do we know what that is?
Yeah.
Sort of.
One way to deconvolve it, you need some kind of model of what the original convolution is, and I'm wondering how good those models can be.
So in truth, we never really know what that original signal was, because to do that, we actually have to travel to that star or that galaxy to get it. So what you typically do is you have lots of stars, and you see what are the differences between them, and we think they're the exact same type of star. And so we look at the spectrum of this star that might be closer, and we look at this star that's farther away, and we infer the difference is because of the material between us. Okay, so we do that. We also can use the fact that different things. So for instance, what causes a lot of the effects in the interstellar medium, so between us and other stars, is dust, right? You have a cloud on Earth, you can't see the sun, right? Same thing. We have a cloud in space; it's blocking our view. It's blocking our view in the optical, but in the infrared, especially the far infrared, it's actually emitting, okay, because it absorbs that sun star light and then it re-emits it at longer wavelengths. And so you can look in the longer wavelengths and see where it is and map where it is and try to account for that. Now there's issues with that because your resolution in far infrared isn't as good as an optical, so you'd have trade-offs with that. But yeah, so there are things like that. The atmosphere, what it does, we can try to model that and remove that. That's actually a very active area of research because of exactly what you said, that trying to measure how the things get distorted and what we call lensing. You have to know very well that those effects weren't caused by the atmosphere or weren't caused by your detector, and so you spend a lot of time trying to worry about that. So some of the best characterized CCD devices are ones that astronomers use because they do test after test trying to figure out, are they good? In fact, there's actually conferences devoted to trying to understand how well CCD devices can be made to actually give the response you want over the full focal plane of the telescope. Okay, so we have that. So here it is, right, the dark energy survey, right? 70 of those 4K by 2K CCDs. These data totals aren't right, they're actually too low. The data is taken on a remote mountaintop in Chile. It's brought up to NCSA, and it's wanted to be processed within, what, a minute or 2 minutes. Okay, so you have to transfer all that data, you've got to process and do it. And you say, why? Well, the reason why is because if you take a picture and something happened, and I'll show an example of this later, one of these transient events, you want to know about it immediately. Because we have things that will decay on timescales of seconds. So they only appear and they're gone. And so if you don't know about it within a minute or two, it's too late. You'll never be able to get it again. And these are rare events, we want to be able to find those, so we need to be able to process them right away. This actually started taking data about 1.5 years ago. We've now just finished taking the second year's data. It's a lot of data, and after about 5 years, it'll cover about 1/8 of the entire sky. This is actually in the southern hemisphere. This lone survey I showed you earlier was in the northern. To give us sort of sense of scale, here's the full moon. Okay? And since there's not a lot of landmarks up in the sky, about the only one we have is the moon, to give people a reference. That's something I'll show you repeatedly, right? So you kind of should have an idea roughly, your fist at arm's length is about the size of a full moon. That's roughly how big of an image we get there. All right, there's future surveys coming, LSST. Again, Illinois is a major partner in fact, they just got, I think it was a $70 million grant to start doing some work on this. It's a lot of money. And then there's another survey, the SKA, which is even farther out, which will be literally generating so much data that the data will be taken in maybe Australia or South Africa. Those are the two leading sites. And Cisco is a partner in this, and they actually are planning on having a ship that goes, and they put the disks on the ship, and the ship goes around the world and drops data off. Yeah, I mean, this is Cisco, a networking company, that this is their solution. It's just too much data.
What's the funding status of SKA?
SKA, I'm not completely familiar with that because it's an international body, and so different parts of the organization have committed. The U.S. has committed some, but I think it's primarily still in their R&D phase, trying to figure out what we're going to do, because they haven't finalized the sites. They're still trying to do all of that. But Athol Kemble in the astronomy department is involved in that. You can certainly answer that question. That's a radio survey as well, so that'll be. And the goal is to build lots of little dishes that total have the collecting area of a square kilometer. So you could try to build something that was 1 square kilometer, but that would be very difficult engineering-wise. It's easier to build smaller ones and stitch their signals together. Massive correlators for that. Okay, so now I want to start actually looking at some data and show you some of the things we're trying to do. So this is an image a student and I made. This is actually a coma cluster of galaxies. Again, looks great, but you're like, okay, well, how big is that? Okay, so I told you, right? We would show you full moon. There's the full moon, right? This entire cluster of galaxies would roughly fit behind the full moon. This cluster of galaxies is about 100 million light years away. It's one of the closest big clusters of galaxies to us. I'm going to zoom in on this one part here. So this is actually this data. You can go and look yourself off the Sloan Digital Sky Survey website. This is the color JPEG image they made. They took the multiple bands they had and just made a color image out of it. So you say, great, that's useful, but we don't do science off of the image. We like to have catalogs. So they run a software pipeline they built and detected sources. Okay? Now the astute among you notice, oh, there's that little symbol I put in there, right? We've now entered the realm where new ideas are needed. And I'll try to show you what I mean here, right? So you can see, well, there's a lot of things detected there. Yeah, that's fine. But if we start zooming in, we start to see certain issues, right? Here is a bright star. And you notice these color offsets. That's because we've combined images taken in different filters, and there's little scattered light problems, those sorts of issues we have. And if you look over here, it can cause issues, right? There's like 20 sources detected right in the center. Well, there's really only one. It's one big bright star. So that's a problem. We also have this thing, right? That's actually probably a satellite passing overhead when the image was taken. All right? Notice it's only in one band, only in the R band, so that they pass over pretty fast. Another one is here, right? There's this really pretty galaxy here, face-on galaxy, and it's been broken up into lots of things. Okay, so source detections are easy to find. The one little isolated object by itself, we often don't have that situation. So finding things, removing them if they're a problem, dealing with that's a problem. Here's another one, right? So I've zoomed way in. Here's a bunch of objects that are very close together. In green, when the pipeline goes around, it says all these pixels in the image, they're part of an object. And then it tries to break them up into little objects if it thinks it needs to. Okay? And, okay, that seems reasonable what it's doing. But, again, here it took one object and split it into two. There's only one object here. And as I show you in the next slide, it sometimes does even worse. Right? Here's that big nearby bright galaxy, M101. And it turned it into thousands. Right? Because it's supposed to find small little things, and so it found lots of small little things in that big galaxy, which of course are actually stars in this nearby galaxy. We can have that confusion, we can have multiple detections. We can also have this problem of detection in images. So we look right here, it finds this object, but it finds some things that are probably spurious near it. And then we have something like this object, which is finding things it shouldn't. And then sometimes not finding things it should, especially if you're near a bright object. So there's issues there that we have to try to fix.
So how do you know? How do you know if you've had a misdetection?
How do we know what?
How do you know your ground truth in your detection? So you have a detection scheme, and you're
so the question fundamentally is if we had a truth image, and then we ran our detection software on it, yeah, we could do that. You're right. We don't. What we tend to have though is an image taken with a different telescope, maybe in certain areas, and so we do know sources that should be detected that weren't. Sometimes you can actually go in and by eye, you can see it.
So is the ultimate goal to improve your detection scheme so that you can do this without having to check it?
That would be one goal would be to do that, yes. Yes. So we actually are working on this. We actually are exploring some Bayesian techniques by making fake images and then running stuff on them. The problem is it's extremely computationally intensive. But hey, we got a supercomputing center, right? So we can do that. So this is we use a multi-nest Monte Carlo Markov chain technique, nested sampling, and it's looking promising. We also are doing the same thing for characterizing the sources themselves, trying to do a better job of that.
So does it help to take models of different kinds of objects rather than, it looks like your object detector is just detecting points of light.
Fundamentally, that is what we're trying to do, right? Fundamentally, we're just trying to say, is there an object here or not?
Yeah.
Then we actually say, what's the best model to fit?
But it looks like, I mean, a lot of the problems that you're describing look like they're problems where it's breaking up an object that doesn't fit that small round dot of light model. So would it make sense to instead have a spiral galaxy face on?
You might think so. You might think so. But when you do these sorts of problems, it's part of the reason why that processing pipeline worked the way it did. You optimize to find the majority of your sources. There are not that many nearby galaxies, right? They cause problems. And so what you tend to do is you just say, there's a big nearby galaxy here, we ignore it. A bigger concern is when you get these objects that sort of, like this here. This raises the local background. You can kind of see that, right? It's got a fuzz around it. And the techniques that are used are you estimate a background, you subtract it, and you say, is there something left over here? And so when you've raised the local background from the global mean background, you tend to cause problems. They tend to have issues with that. So you would want to be able to model that full light distribution. But it's complicated because you have this, the atmosphere blurs things, and as things start blending into each other, and so source to blending is a real problem.
So from a signal processing point of view, the tasks that you've shown in the last few slides would fall into the category of detection. That's one problem. And the other one has to do with classification or clustering. So you were doing some of that. For example, the example you showed where the spiral in the galaxy, your essentially classifier ended up with having too many classes that were not realistic. So how are those two problems, detection and classification, how are they related in the ultimate goal that you have here? In other words, what is the ultimate goal? Once you make the detections or classifications, how are they going to be used?
I'm just about to talk about classification. So you raise a good point. Fundamentally, the first step is detecting things. Sometimes we don't have sufficient signal to actually do a classification. We just have a detection. So it's not a case that we can do both all the time. Whenever you can, you want to try to have some reasonable classification. And one of the benefits we have, I'm not sure if you were here when I started, but I talked about the multi-band nature of our observations. We have these multiple bands. So you can use the fact that something is detected in one band but not another to infer that perhaps it's farther away, and that can help you in your classification. So you can use extra information to try to help you with this problem. Fundamentally, we want to know everything that's out there. We want to know what type of object it is. We want to know how far away it is, right? To do that, we really want spectra of everything. And that's what I was talking about at the start, right? You can't get spectra of everything. And so that's a problem. So going to this issue, right, source classification, fundamentally, we think about things, there are two things we worry about. Is it a star? Is it a galaxy? Stars are in our galaxy, right? I'm a person who studies distant universe. I don't care about these, right? One star I really like is our sun. And so we want to get rid of them, but the problem is, right, this is a measure of how bright an object is, and astronomers like to do things different. So this is the brightest. The small number means it's brighter. Big number means it's fainter. And so as we go left to right, we're getting fainter, fainter, fainter. This is actually a logarithmic unit as well. So 5 units is actually a change of 100 in actual flux, luminosity. And so you can see that here, yeah, the galaxy looks a little more extended, but then we get to about 19th and 20th, they start looking the same. If I was really cruel, I could have given you a quiz. I said, you can't leave until you actually can tell me the difference, right? Which one's a star, which one's a galaxy? So this is a problem that we're facing, okay? And this is true of any survey. And it's compounded by the fact that the number of objects is a function of this unit of brightness increases exponentially, right? Which kind of makes sense because the farther things are away from us, the dimmer they appear, and that volume of space is growing with our cube. So you can just think, right, it makes sense. Even in a simple Euclidean universe, it's going to happen that way. There's always many more objects down here than out here. And so this goes back to the problem of, well, are you just trying to detect or are you trying to clear? Well, first we just try to detect. Then we try to use some way of trying to classify what we have. So this is the first thing we're trying to do. And it's actually a mixed distribution. We got some mixtures. So we do different things we've developed. We've developed an augmented random forest technique to do this. We introduce even more randomness. We developed a unsupervised analog of a random forest called a random atlas. We use self-organizing maps. So a map is the same as a tree in the forest, and we randomize these, we combine these together, so we get an unsupervised prediction. We also build models, template models, and compare that. So we're doing Bayesian models. We then combine them together. We even combine them together differently in different parts of parameter space. So this is a hierarchical Bayesian combination. And we can get decent approaches, but we still need to do better.
So these classifiers that you described in the last 5 slides are are the different bands that are available in any one image?
Yes. So no, different bands of the same part of the sky. So you've taken a picture of the same part of the sky. So each object, you have a measure of its brightness in different bands.
So this is one pixel, or this is the little pixels?
This is not a pixel. This is an object.
Okay.
One of the things we're actually exploring is, can we do this at a pixel level and then somehow coherently combine it together into a detection measurement and a prediction measurement?
Okay.
It seems odd. Well, wouldn't you do that? Well, because it's already bad enough when we have 1 billion sources, and then I say, great, now you just give me 100 billion pixels, and I've got I got to do all this on them. So there's some issues there. So each of these filters we have a measurement for. Typically it's about 5. Right, and you can see that here. Here's an example, right? Here's your flux measurements, and here's a fit of a template spectrum to it. Okay. All right, so we do all that. Sorry for going through that fast. I can always share the slide and talk more about that if you want, but I wanted to get the synoptic part. But that's only one part, because we don't want to just say, is it a star or galaxy? That's useful, but it's not as useful as knowing more details. So we want to know what type of galaxy it is. And galaxies come in different. If you saw that image, you saw some that were elliptical-like. They had that fuzz around them. Others were the spirals, right? Beautiful spirals, maybe face-on, seeing things. And that's important because not just do they look different, they actually have a different evolutionary history. Different things are going on. Ellipticals tend to be old stars, not a lot of new star formation. Elliptic or spirals have a lot of newer star formation. Okay, and so that's telling us something about the evolution of those galaxies and their environment. Yes.
Suppose a galaxy is head straight on, perpendicular to our image. How do we get an angle to see if it's,
we don't.
We don't.
The problem is if you take a spiral galaxy and you turn it, you just get this long thin thing, right? So the question is, what do we know about that galaxy? We only know what we can observe.
Okay.
You can sort of do other measurements. If you really want to know, you can start inferring from other measurements what its rotation is. Does it have a rotation like a spiral? So then you can say, yes, it's a spiral. If you see some sort of bulge, you might also have the fact that, okay, like you're seeing an egg, you can see the bulge in the news. You might be able to infer things like this, but we can't. If it's slightly inclined, you can start to estimate the inclination based on a measured rotation. But that is hard. For most sources, we don't do that. Okay, we just classify it on appeared morphology. All right, so here we go. Here's a problem, right? This is that same image I showed you again before, right? So this is smaller than the full moon. And in here there were 10,000 or more sources, and we have, I don't know, 100,000 images like that. So it's a lot of sources. What do we do? This was one of the originations of crowdsourcing, right? Right, I showed you at the start, everybody loves astronomy, right? You want to be in your spaceship and travel, right? So this was the thing. They did this, the Galaxy Zoo. They used the same data I'm showing you, showed it to people, and were shocked at the response, right? No payment, no nothing. You just put the images out there, and you have 100,000 people classifying images. Right? Now, that opens up a whole other, if John Ming was here, I could have him stand up and talk a little bit, because this is a whole new research area that I'm doing with Tom's group, right? We have people classifying these things. Who says they're doing it right? Right? You have 50 people classifying the same object, they all don't say it's the same thing. How do you use that information, right? So we actually have a proposal pending to do that, or have a paper that's going to go in soon talking about this. So it's actually really interesting information theory, thinking about how do you combine that. I like to say, who are these people doing the classification, right? They're people all over the world who work, they come home from, have dinner, deal with the kids' homework, have a glass of wine, sit down at the computer and start classifying galaxies. Literally, right? Some of these people, they've actually been interviewed. And so you think, well, I might like their classifications, but after that first glass of wine, maybe not, right? Or maybe that second glass of wine, definitely, we don't trust them anymore. But we don't have that sort of personalized information, so we have to try to infer it statistically. And you do that by doing aggregation, comparing across time what they're doing. And that's the beauty, is that there are hundreds of thousands of galaxies that have been classified by them. So, averages like 42 people classifying each of these things. you actually have a lot of statistics to start trying to play with these things. So that's a really interesting thing, and one of the main things, the reasons I come over to Beckman is to work on those projects with them. All right, but there you go, citizen science. This then developed into the full, what's called zoo universe. Maybe you've seen it, and now it's branched into other fields, all kinds of having people look at data and classify and stuff. And we use that. So again, just to remind you, it's a lot of data of the sky. It's an image that's made by just saying, where are all our galaxies, and trying to plot them on this 3D structure to show you the sky. So this is about a third of the full sky Sloan is covered. And now when I say they've taken a picture, that doesn't mean they've gotten everything, because Sloan only can observe down to a certain flux limit. If things are too far away, they'll be too faint to appear in our images. They'll be too low signal to noise. We also use machine learning algorithms to do distance estimation. That's all this slide was trying to do. And again, we combine different techniques. There's new things described here. This is an incredibly important problem, because if we're trying to infer where like dark matter is and things like this, we have to be able to estimate where how far away these galaxies are. And so there's a lot of work that is being done here in these projects that I'll talk a little bit about. Okay, so now let me switch to synoptic astronomy. So what is synoptic astronomy? Synoptic astronomy is where you take a picture of the sky, and then on some other night you come back and take another picture of that same part of the sky. And then maybe you come back some other night and take a picture of that sky, and you just keep doing this. Now, we always do this in astronomy. If you think about it, if you take a picture, sometimes there's literally crap in our pictures, okay? We have charged particles that are coming through the sky, they'll hit us, there might be a satellite trail, there's CCD defects, whatever. We always want to have multiple images that are slightly shifted around so that we can co-add them and remove those defects, one of the ways we try to account for instrument defects. So we always do that, right? And this is showing that. Here's 4 pictures of this star cluster called M38, right? We then statistically combine these images together to get a deeper image. So we're stacking them, so our signal to noise goes up in the image. And you can see, here's the stacked image, right? There's a lot more detail here, because you've summed the signal from 4 different images, all right? Another example, here's another Messier object, M42. We have 31 images over here of this. These are actually from amateur astronomies. Astronomy is a wonderful science. We have a bigger amateur community than we do professional community. I took these pictures, you combine them together, and the change in the detail is amazing, right? You've been able to see much lower surface or signal parts of the signal, lower surface brightness features, because we've done this co-adding. So we've always done this. The difference is now we start to look at what happens if rather than adding them, we subtract them or simply see the deltas, okay? And that's where we're going to now in synoptic astronomy. So here's a picture of another stellar cluster, M3. It's a color image. We've taken images in different bands, added them together. And if I do this, and you look carefully, you start to see the Christmas tree, right? You see the lights blinking on and off. Those are actually stars changing their brightness over time, all right? You see this here, this star here, this star here. You'll notice predominantly these bluer stars, this one here is showing a little bit, getting brighter over time and going dimmer. All right? Now, that's a nice acute visual, but it doesn't show you that statistical signal. Here's another one. This is a Type 1a supernovae. This is a nearby galaxy, Centaurus A, big dust lane through this elliptical. Here is going to be its light curve. You'll see how bright it gets over time. Here's its spectrum. So you can also see how its spectrum changes. Okay? So you look, supernovae goes up. Right here, it gets dimmer, right? You can see it gets brighter on its light curve, it gets dimmer. You also see its spectrum changes over time. So this is why we need that very quick identification. We take an image, we then want to process it very quickly to see, did something change? Because if we have a supernovae, we want to catch it as fast as we can on its rise so that we can sample this with other telescopes really well. Okay? So we have to be able to notify that really well, because that rise time can be a matter of days. Right, so you want to be able to get that and get on it. And again, if you find it today, you may not be able to get other telescopes to look at it until tomorrow. And if they're weathered out, it may be 2 days. So you always want to try to get that announcement as fast as you can out. So that's a Type 1a supernova. Those are extremely useful. We use them as cosmological probes. Here's another example. This is now for exoplanet studies. If you have a star and a planet is going around you and it's inclined such that you are looking along what's called its ecliptic, its orbital plane, the planet goes in front of the sun. And then the planet goes behind the sun. And when that happens, okay, you'll notice, here's the thing, you get this decrease in the brightness of the star that you're measuring. That's because the planet effectively went in front of the star. You also get another little decrease as it goes behind because the planet is actually re-radiating some light. And so you get this other decrease. And so by measuring this, you actually can get an infer of the size of the orbit. You can get an estimate of the mass of the planet. And then if you assume something about the mass, and you also get a size of the planet from these, you then can assume sort of what type of planet it is. You can then put it on that habitable zone planets that I was showing you earlier. This is the way Kepler works. So anytime you hear about a planet detected by Kepler, this is what it does. Now, I knew about this. I thought this was pretty cool, right? We find planets. What I did not know was the level to which they had pushed the analysis of these light curves. These are light curves. They take pictures over and over and over again, sometimes the same part during a night. They now are to the level of sophistication that they actually are measuring what's going on in the atmospheres of these exoplanets. It's amazing, because they'll use things like here, as the planet's going around back over here, it's now reflecting light from the star as well. The planet has a wind, so it's moving around, so you can actually start to see what's happening to the atmosphere of that planet. You can measure differences in the temperature of the side of the planet facing us and the side facing that star. I thought that was pretty amazing. We're not just detecting exoplanets, we're talking about the atmospheres of exoplanets. That wasn't even the total coolest thing I saw. We had a series of people come through last semester giving us seminars on exoplanets. They actually are building models for the interiors of exoplanets. And they can constrain those from these measurements as well. So it really is amazing. I mean, you know, like I say, 5 years ago, couldn't we just find some other exoplanets? Can we find exoplanets that might be in the habitable zone? And now we're talking about trying to understand the dynamics of the atmosphere, trying to understand the dynamics of the inner parts of these exoplanets, all from these synoptic observations, which is just taking a picture with a telescope, and taking another picture, and taking another picture, and analyzing it.
Are these spectroscopic measurements?
No, they're
white light.
photometric.
The
Purely
white light.
just an image. They're through filters. You tend to do it through filters. I'm not sure what Kepler's is, but different telescopes use different filters for that. One issue that you can do here is stars tend to be very bright in the optical, and the planets are obviously not. They're not emitting in the optical, but they are warm in the infrared, right? Like the Earth is giving off energy into space, right? That's why on a winter night when there's no clouds, the Earth cools off so much. It's emitting its light. The clouds act as a blanket to keep it in. So the planets actually do get brighter in the infrared. The star generally gets dimmer in the infrared. So often these observations will be done in the infrared because the star will be much dimmer there.
I have a question.
Yes.
We know what, like all the atmosphere and what we have about Earth, and we have, probes almost at the edge of the solar system. Do we do this experiment as a control on the Earth?
Yes. Yes. Typically not with the Earth because we don't have a lot of Earth-like analog exoplanets, but you do it with Jupiter, you do it with Saturn. So Cassini is out there, has done. We've had missions fly by these, and so we do get observations of those. One of the, what was this, 2 years ago, I think it was, Venus transited the sun. And a lot of people was like, why would you care, right? It's kind of a cool little thing. This planet goes in front of the sun, you can study it, but that's just what this is, right? And so it was very heavily studied to make sure you could calibrate things really well. And because they did, that's how they can start to infer all the tiny little bumps and wiggles on these light curves as being things like atmospheres and interior dynamics and stuff like that. So to the best effect, yeah, there are still a lot of model uncertainties, right? And knowing what I know a little bit about statistics, I was able to ask some questions that, okay, maybe we shouldn't be quite as excited as we thought, but it's still, to me, it blows your mind to even think you could have a graduate student do a thesis on what's the interior of a planet around a star. It's pretty cool. So this is, actually plots I made. This is synthetic simulated data for an assumed black hole with material accreting around it. What are different types of light curves you may get, right? This is not something we would get because we couldn't sample it this frequently. But the black holes are stochastic. They're stochastic events. Okay, there's damp random walks if you want to think about it like that. So you can think about it in terms of light crossing this thing. You can think about it as material orbits around the black hole. You can think about thermal timescales. So these are different sort of things you can do, and then you can take observations of real black holes that we have in the optical and see their variations. Okay, and then try to model what they are, and then infer what would be the mass of the black hole. This is pretty new stuff that we're trying to do. We may be doing more of that. But then you think about this, you're sampling at different times, and that's fundamentally an issue. You introduce aliasing and all kinds of stuff. So this is another example of that. So this is similar to the light curves I just showed that were simulated, but this is real data now. And remember, I told you one of the things we want to do is find these objects that have been multiply imaged. The reason is because as they travel on their different paths, they go different physical distances to get to us. Okay? And because of that, they actually are ways to probe how far away things really are from us. It seems an easy question, right? What do you mean, how far? Well, all right, I can't have a student take his thesis and lay meter sticks down and actually measure physically how far something is. Okay? We can't. We always have to infer ways to get distances. So these ways, these different paths these are taking, the light curves are all different. So if something goes up like this and then comes back down, on one object we may observe it here, and then we may observe another one a week later, and another one a month later. Sometimes it's years. So we monitor these objects when we find them, we monitor them, and then we figure out the shift, and that tells us the relative distance that those travel, right? Speed of light times time, you get that distance. So that's really important to be able to get these, because that tells us all kinds of things about what's going on in these events. This is an object that's four image ones, and they've been shifted, so everything lines up. Same thing here. But these both, this one was around 450 days, and this one was around 300 days, time difference between the maximum and the minimum. So you can see you have to observe over a number of time, and you do. These are days, so this is 53,000. We use a Julian day, 53,000, and this is 56, so that's 3,000 days, right? Roughly 8 years of observation to get these sorts of data sets. But we do that, then we can actually start modeling. So here's examples of some of our signals. If you look at this, you immediately notice some things, right? There's a gap. What, did somebody forget to turn on the machine, or what's going on? Right? Well, remember, we only observe objects at night. If an object, as we go around the sun, right? So I'm looking at an object, it's over there, the sun's over here. 6 months later, I'm on the other side of the sun. That object is up when the sun is up. I can't look at it. So there's a period of about 3 to 4 months, we just can't see the object. So we get these big gaps. If our feature we're trying to line up is in those gaps, we're in trouble. There's also periods like here you'll notice, where there's gaps. That's simply a case of, it was cloudy. The telescope wasn't working, we didn't have the telescope that night, something else. You also notice that some of these data are pretty good. These are pretty ratty. Sometimes we're very low signal to noise. So we end up with aliasing effects. We have non-uniform sampling. Aliasing effects, we often have non-Gaussian errors, because if we're down very low to the signal to noise, you can't go below 0. So right, if you're 2 and your positive error is 3, you can't go to -1, so we can have non-Gaussian errors. That's a crude way of describing it, but we have these problems. So this is a challenge. So not only do we have the problem of trying to find these, I showed you that picture and I said find them, right? Right? That's a challenge finding them. But once we find them, it's an issue.
Were you trying to answer a specific question about gravitational lensing?
Yes.
What is that?
I'm trying to understand what is the actual distribution of dark matter that's causing this object to be imaged the way it is. And then I also am going to use the fact that I have these time delays as probes of dark energy. Because if I know that at true distance, and I have many of these systems, I can actually probe what that change in distance is, just like you do with supernovae. And so I can map out the evolution of dark energy in cosmic time. So the problem is we only have a handful of these lens systems like this. Okay, but surveys like this, the LSST, leading me into one of my final slides here. LSST does 2 Sloan surveys a week. Right? So all that stuff I showed you up until a few slides ago was from the Sloan Digital Sky Survey. It was like roughly a 10-year effort, right? Fundamental change in astronomy. We had this huge, rich data set. It was great. But this project that we're building, and the data will be processed and archived just across the street over there, right? Petabytes of data a year. Fundamentally will be even better, because it literally is a Sloan every few days. It's a huge telescope, 8-some meters. Sloan was only 2 meters. And it takes pictures every like 15, 20 seconds. Okay, so literally just going to take picture. And it's going to change the way we do things, because now, if you think about it, we had that whole Sloan survey, and then we come back a few days later, we do it again, and we keep doing that for 10 years. We literally will have movies of the universe, right? And that's where we really get into this synoptic astronomy. And so that's what we're trying to do now, is trying to prepare for this. So no longer am I simply trying to detect, 10 billion sources. I'm trying to detect and model them every few days so that I can truly understand and build this signal. Now, this survey is supposed to start in 5-6 years, something like that. I'm, 5-6 years, and I throw on it's a 10-year lifetime. I'm actually at my retirement age, assuming our state government doesn't do something about that. And so I don't want to wait till the end of the survey to think, oh, I've got my signal now. I can actually do my science. Right? It's only been 15 years, no problem. We want to be able to do this as quickly as possible. So that's the other challenging thing here is how fast can we identify objects and classify them. Fortunately, there are a number of precursor surveys that have been done, much smaller telescopes, so they don't go as deep, they don't have as many sources. We have one that we're working with now that's about 500 million sources, and there's several hundred points in their light curves typically for those, so we're trying to analyze those. But the beautiful thing is that LSST is going to allow us to look where we haven't even looked in parameter space. And any time in astronomy we look in some area of parameter space, we start finding things we didn't know about. Right? The universe is crazier than we thought. So these are just some examples. We take some images. We suddenly have optical transients, things that can pop up, only be there for 15, 20 seconds. They can disappear. Here's an example of another one. You can just see these, the difference image. Here's one. Here's a second, and there's just a difference image. We have things moving. Obviously, we would like to know about near-Earth asteroids. You would want to know about these as well, because if it comes too close to Earth and hits us, we die. We go like the dinosaurs. So we'd like to know about this. We have a pretty good idea of the really big ones, the ones that would just destroy everything on Earth. But things like the thing that killed the dinosaur, we don't. Right? There are still ones out there that we don't know about. And if they're moving around on a collision course, we kind of like to know about that. The more warning we have, the easier it is to do something about it. And no, we're not going to take a comet that's about to hit Earth and split it in two and have it go around. If you've seen that particular movie, Hollywood movie. So all of these things are done by actually having these repeated imaging, right? So it's really opening up this new vista. And there's a lot of opportunities and a lot of ways that things can be improved. This is just showing examples. This is one of these precursor experiments we're starting to play with. I used to be at Caltech, and some of my colleagues there are leading this, and they were just contacting me last year and said, look, we have way too much data. Can you please help us? So we're starting to look at this. And so we see all kinds of light curves like this, right? These are really strangely sampled. This is small telescopes all over the world, and when they get a chance, they actually get the data. Again, non-Gaussian, non-symmetric error bars, a lot of aliasing and trying to find things. They actually went in and found about the first few million things that were easy to classify. They did that, and we're looking at the other 99% of the data. Trying to understand that. And this is just interesting. This is a sky map. It shows you how many times they've observed each part. So anywhere from 600 down to 20. And you notice most of the data is up in here, which is a few hundred points. So that's some interesting stuff. And I can talk more about that if you want. So just to finish up real quickly, what I wanted to sort of talk about, this is an actual, there's national, international collaborations. This is one that would be the most relevant for anyone here, would be this informatics and statistical science collaboration. And this is just a boring PDF page that I'm showing here, but there actually are collaborations between statisticians, computing people, informatics people, and astronomers, all trying to do these things with the realization that these are, these signals that are coming out that we need to be able to do classification on. And if you have any interesting thoughts or ideas, I'd be interested in hearing. So that I'll stop. Apologize if I went a little long. It took me a while to find the right room. So it started a little late. But literally, we have opportunities from the telescope to the disk, and the one that I sort of focused on here today was this one, the Synoptic Astronomy. So thanks, and if there's any questions, just let me know. You got to do something like that. It never changes.
Yeah, that's so that you don't feel like you've overshot your
Yeah,
time.
well, that's what I said. I realized this. It was like 10 minutes in. I go, wait a minute, really?
Well, thank you. I guess we're over time and everybody.
Yeah, we got to go. Or what? It's snowing out. You got to be careful.
So I'll ask you one question.
Sure.
So the first part, when you were talking about detection and classification of the